Hello and welcome to this lesson for OCR A-Level Physics in Module 5 Newtonian World and Astrophysics on the topic of gravitational fields, looking at the concept of gravitational potential difference. So if we've been successful and we've learnt in today's lesson, we should be able to define what gravitational potential difference is and why it's important when work is done, calculate the gravitational potential difference for various scenarios, and understand what equipotential surfaces are and their importance in fields. So we're going to be looking at 5.4.4 gravitational potential and energy for OCR A-Level Physics. So if we consider a massive object inside a gravitational field, when a massive object moves in a gravitational field, work can be done. Now this can be calculated by considering the change in gravitational potential in the field. So as you can see here, when an object moves between different potentials, work can be done. Now if we consider the following gravitational field. Now the dashed lines in gravitational field diagrams represent the different potentials found in that gravitational field. Now objects can move between different areas of gravitational potential, and this requires work to be done. So we say that the object has moved due to potential difference. Now the potential difference, or delta V, is calculated by working out the difference between the potential areas the object has moved between. So in this example, delta V is equal to minus 240 minus 120, which is equal to minus 120 joules per kilogram. So we can say that the potential difference is the work done per unit mass needed to move an object. This is because the gravitational potential is the energy at each level per unit mass. Now remember that the potential becomes less negative as the object moves away from the object producing the gravitational field. Less work needs to be placed into the object to overcome the gravitational attraction and leave the field to have its potential become zero. Now this works as gravity is always an attractive effect. So this gives our equation of delta V is equal to delta W over m, which we can rearrange to say delta W is equal to m delta V. So this equation tells you the work done needed to move an object between 2 points of different potential in the gravitational field. Or you could say it's the work done needed to move an object over a potential difference in a gravitational field. Now the m term in the equation refers to the mass of the object moving, not the mass of the object producing the field. So as we said before, this equation will tell you that the work done needed to move an object is directly proportional to the potential difference if the mass of the object remains the same. Now we can also write this out as delta W is equal to m delta V is equal to minus gmm over r from using our previous equations. Now when a mass is moved against the force of gravity, work is done. So the work done in moving a mass m is given by the equation delta W equals m delta V, where delta W is the change in work done, m is the mass, and delta V is the change in gravitational potential. This change in work done is equal to the change in gravitational potential energy, and when V is equal to 0, the gravitational potential energy is equal to 0. So the change in gravitational potential energy, or work done, for a mass of m at a distance r1 from the centre of a larger mass m to a distance of r2 further away can be written as the following, as minus gmm over r2 minus gmm over r1, which can be simplified to be equals to gmm 1 over r1 minus 1 over r2. Now, work is done when an object in the planet's gravitational field moves against the gravitational field lines, i.e. moves away from the planet. Now, moving away from a surface of the Earth, in this example from A to B, there will be an increase in gravitational potential. So we would say any object moving this way would gain gravitational potential energy. In the same diagram, if an object moves from A to C, there is no change in gravitational potential, so there's no change in gravitational potential energy. And in this diagram, moving from B to A results in a decrease in both gravitational potential and gravitational potential energy. So here is an example question regarding gravitational potential difference. A forklift truck does 2120 joules of work to increase a pig's gravitational potential by 26.5 joules per kilogram. What is the mass of the pig? So the first step is to write out the equation. M is equal to delta W over delta V. Placing our values, so 2120 over 26.5 We calculate our value, which is 80, and we give our value to the appropriate significant figures in with a unit, so it's 80 kilograms. Now we can represent the idea of gravitational potential difference with the following graph. And the area under the line for this force against separation graph gives the work done needed to move an object through a gravitational field. So we can link the force separation graph with the changing distance of an object from the centre of mass of an object like a planet. The work done to move a mass up from B to A, i.e. the object gains gravitational potential energy, is shown by the shaded part of the graph. Now the work done can be negative if the object moves or falls from A to B and it loses gravitational potential energy. So as we can see in these diagrams, the dashed lines show the plane of the gravitational field where the gravitational potential is the same. So in this diagram we call these lines of equipotential, and they're like contour lines on a map. So as the potential along the line is always the same or equal, we call it the line of equipotential. Now work is needed to be done to move an object between planes of different potential. There is no change in potential along a line of equipotential. So if an object moved across this equipotential line, no work will be done. So work is needed to be done to move an object between planes of different potential. There is no change in potential along a line of equipotential. So this means a mass can travel along an equipotential line without any energy being transferred. If an object, such as a satellite, moves along an equipotential, its potential energy does not change, as there is no movement in the direction of the force, so no work is done. This is also indicated in the equation delta W equals m delta V. If delta V is 0, delta W is 0. Now in radial fields, the lines of equipotential are spherical spheres. Now the lines of equipotential, as mentioned before, are always represented by dashed lines. Now remember that no work is done when you travel along an equipotential line. A mass can travel along an equipotential without any work being done on the line. Now lines of equipotential are found at 90 degrees or perpendicular to the field lines of the gravitational field, and you would be expected to deduce lines of equipotential from gravitational field line diagrams. Now in our radial field, the equipotential is found as concentric spheres, whilst in a uniform field, the equipotential is found as regular rectangular planes. Now this diagram here on the screen shows the lines of equipotential in the Earth's gravitational field. Now equipotential surfaces around a spherical mass will also, as indicated before, be spherical. Now this has big implications for any orbiting body in the gravitational field. The potential energy store of a satellite in a circular orbit around the Earth or any orbiting body remains constant, provided that its distance from the centre of the Earth does not change as they're on a plane of equipotential. Now for a satellite in an elliptical orbit, there is an interchange between kinetic energy stores and potential energy stores, as it's not on a plane of equipotential and is therefore changing position. Now moving to a higher orbit increases this gravitational potential energy store as work is done to move away from the Earth. This comes from the kinetic energy store, so the satellite orbits slower. Whilst moving to a lower orbit decreases its gravitational potential energy store as it's closer to the centre of the field. Now this increases the kinetic energy store so the satellite orbits faster. So to summarise, gravitational potential is equal to minus gm over r at a distance of r from a point mass m, and that leads to changes in gravitational potential. Whilst a force distance graph for a point or spherical mass gives you a work done, which is the area under the graph, and the gravitational potential energy is equal to mvg or minus gmm over r at a distance r from a point mass m. So thank you for listening to this lesson. If we've been successful and we've learned in this lesson, we should be able to define what gravitational potential difference is and why it is important when work is done, calculate the gravitational potential for various scenarios, and understand what equipotential surfaces are and their importance in fields. So thank you so much for watching this lesson on gravitational potential difference, which is part of the gravitational fields topic in our Module 5 Newtonian World and Astrophysics for OCR A-Level Physics. Thank you so much and have a lovely day.